Module 5, NBTS in Crop Sustainability.
New breeding techniques are a suite of methods that could increase and accelerate the development of new traits in plant breeding. They often involve genome editing to modify DNA at specific locations within the plant's genes so that new traits are produced in crop plants. NBTs and, in particular, advancements in genome editing technologies have revolutionized the crop improvement. CRISPR-Cas9 is a multi-purpose technology for genetic engineering. CRISPR-Cas9 has been successfully used to obtain plants resistant to biotic and abiotic stresses, with improved yields and nutritional value, such as vitamins and micro and macro elements. The challenge of new breeding techniques is to ensure the ability to design innovative crops for sustainable and healthy agriculture. New breeding techniques are molecular tools that can create, increase, or accelerate the development of new traits in plant breeding. The first breeding techniques were based on the induction of mutations with physical or chemical agents. Later, thanks to the discovery of PCR as a molecular biology tool, more and more precise systems were used, such as RNA interference, transgenesis, up to the use of genome editing. New breeding techniques modify DNA traits, causing changes from the scale of single-base modification to the insertion or removal of one or more genes. Using mutagenesis or transgenesis to create a new variability, DNA modifications occur randomly. We know what we want to change, but don't know where it happens. The unique feature of genome editing is the possibility of gene manipulations, including gene knockout, gene replacement, base substitutions in specific and targeted sites. Genome editing is based on the use of programmable endonucleases that act as molecular scissors, able to digest the double helix of DNA at a precise point. DNA double-stranded break, DSB, leads to activation of cellular repair processes. The cell repairs the DSB in two ways through the system: homologous recombination, HR, or non-homologous end joining, NHEJ. The cell repairs the breaks, but in doing so, it introduces with a certain frequency of errors, what we call editing events. Classical mutagenesis introduces thousands of random mutations, while genome editing generates individual specific mutations in a target gene. Another advantage is that selection is faster. There is no need to screen a large mutagenized population, and no backcrosses are needed to remove unwanted mutations. The most common genome editing techniques are mega-endonucleases, zinc finger nucleases, ZFNs, transcription activator like effector, TAIL, nucleases, TIALINs, and clustered regularly interspaced short palindromic repeats, CRISPR. CRISPR-associated protein 9, Cas9. In particular, the ease with which CRISPR-Cas9 can be configured to recognize new genomic sequences has driven a revolution in genome editing that has accelerated the plant breeding and the ability to respond promptly to new challenges. The CRISPR-Cas9 system is composed of sgRNA and the endonucleases Cas9. The Cas9 protein contains two nucleus domains, the RUV-C domain and the HNH domain. The sgRNA includes the trans-activating CRISPR RNA, TRACAR RNA, and CRISPR RNA, KIAR RNA, and it represents the programming element of the system. CRISPR-Cas9 is a protein complex guided by sgRNA. It cuts target DNA and is repaired via two pathways. Homology-directed repair, HDR, allows precise editing. Non-homologous end joining, NHEJ, creates random insertions or deletions. CRISPR-Cas9 can be delivered into plant cells using agrobacterium cells, a gene gun, polyethylene glycol, or viruses. In the nucleus, the CRISPR-Cas9 creates specific double-stranded breaks, which may be repaired through the HDR or NHEJ pathways. Gene-edited plants are identified from among the regenerated plants through genotyping. Using the CRISPR-Cas9 system, a selection agent is used to select resistant Cali and transgenic plants. Transformation vectors can be segregated out from the mutant genomes via selfing or crossing. Genome editing systems provide a cost-effective, stable, time-saving, and less laborious solution. Also, these methods can be used to evade the GMO law, labeling the products as non-GMO because of the absence of any foreign DNA. The benefits of genome editing in horticultural crops are substantial, encompassing disease protection, stress resilience, nutrition enhancement, and increased yield for food security. Abiotic stresses like salt, drought, heat, cold, and metals reduce crop yields by 50%. Genome editing successfully enhances resistance in staple, oilseed, and horticultural crops. Biotic stress, such as insects, viruses, fungi, and bacteria, can attack plants and cause severe damage. New breeding techniques fight back by making crops naturally more disease-resistant. Tools like CRISPR edit key genes to help plants recognize threats and bolster defenses. CRISPR's success includes editing tomatoes, bananas, apples, grapes, kiwi, soybeans, potatoes, and strawberries through gene insertions, promoter tweaks, and targeted mutations. The European Court of Justice, ECJ, classified all genome-edited lines as GMO, whereas the USA and several other countries classified transgene-free, genome-edited lines as equivalent to conventionally bred lines. To date, most of the countries have already introduced regulations or guidelines for crops that have been subjected to genome editing, allowing their use in agriculture in a similar way as conventionally farmed lines, provided they do not contain a transgene. The application of genome editing technology based on CRISPR-Cas9 has significant methodological challenges that must be addressed to fully appreciate the uniqueness of this technique. The first prerequisite to start genome editing is the availability of whole genomic sequence. In the case it is not available, the application of new breeding techniques is more complicated and severely hampers. Some of NBT's and CRISPR-Cas9 system need to transform plant through particle bombardment, or agrobacterium-mediated transformation, and laborious process of desirable transformed mutated selection and regeneration. Delivery protocols and easy transformation must be developed for the modification of the desired plant in the case of recalcitrant crops. Genome editing technologies, like CRISPR-Cas, enable effective modification of plant genomes to enhance desirable traits without incorporating foreign DNA. The CRISPR-Cas system holds immense potential in increasing crop yields, nutritional quality, and resistance to biotic and abiotic stresses. By targeting key genes involved in stress response, CRISPR-Cas can improve crop growth, development, and adaptability to diverse environmental challenges, ultimately contributing to the development of new germplasm resources aligned with human needs.